our next topic here is equivalent vectors. So we want to know what makes two vectors equal. And it's going to be a little bit different than you might have thought. You might think, well, two equivalent vectors are vectors that maybe lie in the same location and look the same, right? Which is a pretty reasonable guess, but it's actually a little bit different. Two vectors are equivalent if they have the same magnitude and direction. And the thing that I want to emphasize here is that that's all they need. If u and v are equivalent, it does not mean that they lie in the same place. It just means they have the same magnitude and direction. So to finish this little note down here, u and v can be equivalent even if they are in different locations. And so here is an example. Okay. It says show that two vectors are equivalent. Okay. Or show that the two vectors are equivalent. Let's start off by working with that blue vector. Okay. So v here. So v, if we wanted to say find its length, we just need to figure out, let me try and sketch in some dotted lines here. You can see that the length of the base is 2 units long, and the height is 1, 2, 3, 4, 5, 6 units high. So the length of this, and I'm going to write the double bars around it, right, for length or magnitude. There should be the square root of 2 squared, right? That's the base squared plus the height squared, which was 6 squared. And so this comes out to the square root of 40. And if you wanted to simplify the radical, you could rewrite this as 2 times the square root of 10. The next thing that we want to do is find the direction of v. And we're going to have a couple ways that we can actually check the direction here. I'm going to have us start off with the more simple one first, and then we'll come up with another way of thinking about the direction of vectors in a little bit. So the more simple way is if these two vectors are really headed in the same direction, they should have the same slope. So let's just measure their slope. And I'm going to write this as m sub v, just to note that this is going to be the slope of v. Well, again, it rose 6, and it ran 2. So rise over run, we get 3. This thing has a slope of 3. Now let's go ahead and do the same thing, but with w. So the magnitude of w so if we look at how long the base is, we can actually see it's the same length as the base of v. And the height is also 6. So this ends up being the same thing, the square root of 2 squared plus 6 squared, which came out to, what, 2 root 10? That's right. 2 square root of 10. And since we have the same rise and run, we also know that the slope's going to wind up being the same here too. And so since these things have the same magnitude and direction, we know that they are equivalent. Let's go ahead and move to our next example here. So actually we're on to another concept, scalar multiplication. So one thing that is kind of fun about this section that we're going to do here is a long time ago you all learned some operations. right? And so operations are things like addition, subtraction, multiplication. Okay, these are things that we can do with real numbers, right? Okay. Well, we have new objects now, and these new objects are called vectors. And it ends up that you can, we'll see this. You don't want to write this down here where I'm writing it because we'll be filling in this space here shortly. But you can actually add vectors. You'll be able to subtract them. You'll be able to multiply vectors by numbers. You'll also be able to do something called the dot product with two vectors. And so this looks like it says multiplication, but when we're talking about vectors, it does mean something actually different. Okay. And let me see. There's another one that you can learn about at some point, which is the cross product. I don't think this one's in our book, but this is another operation. And again, it kind of looks like multiplication, but it does not mean multiplication. Okay, so let's see here. If k is a real number and v a vector, the vector kv is called a scalar multiple of v. Okay. The vector kv has a magnitude of blank, so I want to point out what we're trying to actually say here. So if you have some vector v and you multiply it by a scalar, the question is, what is it going to do to the length of that vector? Okay. And the answer is, it's going to make it k times longer. So is what I'm going to write here to say k times longer is all right. K times the magnitude of v. Let me actually write that in words though. Kv is k times longer than v. And in our next two bullets here is actually another important point here is, well, what happens if k is negative? Okay, and it does actually do something. Okay, if k is negative, it will make the vector v point in the opposite direction. And by opposite direction, I mean 180 degrees in the other direction. Okay. So let's just write this out in words here. If k is bigger than 0, the direction of kv is the same as v. And if k is less than 0, the direction of kv is the opposite of v. All right, and we'll make a couple sketches here just to emphasize this point. So let's say, actually I'm going to draw two arrows. Let's say this one here is v, and let's pick another one, and I want it to look like it's pointed in the same direction. It looks pretty close, but I want to double its length here. So if the first blue one, again, is v, then this next one here is 2v. Okay. And if we wanted to think about what happens if v is negative, again, it will cause it to point in the other direction. So let me draw in one more vector here. I think it looks like it ends about right here. And hopefully it's going to look the same direction as these two. I think that's pretty close. And so this is minus 2v. All right, and then we're on to another operation, addition. And this operation is one of the most important operations in terms of physics. Okay, the addition of two vectors. Okay, so the sum of u and v, denoted by u plus v, is called the resultant vector. To find u plus v, and then is what we have here are the directions on how to add u and v. Okay. So it says position u and v so that the terminal side of u coincides with the initial point of v. Let's actually start that sketch right now. Right, so here's the idea. If this is one of our vectors, this is its initial point, this is its terminal, and we want the terminal side of u to coincide with the initial point of v. So that means that v is going to start where u ends. So let's actually make sure that we just note that this here is u, and let's sketch in v. And let's make sure we actually get it on the point there. There we go. There we go. So let's say that this here is v. Okay. And so now we're going to figure out what adding these actually looks like. Okay. But also, one way to kind of remember to add them this way is we add them head to tail. So that's what was going to go in the next box here. Head to tail. Okay. Now, again, we haven't added these yet. We haven't done step 2. Step 2 says the resultant vector, which is just the sum of the vectors, extends from the initial point of u to the terminal point of v. So here is going to be u plus v. There it is. So what I've done here is I've included a river here in our picture. I want us to get an idea of why we've defined vector addition to be the way it is. Okay. And so imagine first, maybe you're on a canoe or a kayak and you're trying to get across a river, okay, right? River having this flowing water. Okay. So you head in the direction of that vector u, which is pretty much straight across. But again, you can only paddle so fast. Okay? And let's suppose that this river, it's flowing at a rate that is faster than you can paddle, right? And so that's why this vector v here would be a little bit longer, is again, this water is moving faster than we're able to paddle. But you can also see these are in different directions, right? And so you could imagine if you tried to paddle straight across a river while the current is flowing perpendicular to you, that current's going to push you off in a different direction. And that different direction is going to be the direction of u plus v. So if we just take the vector that represents our velocity paddling in still water plus the vector that represents the velocity of the water, that will give us the vector that will give us the velocity for where we'll actually be headed.